So, good afternoon to all of you, and we are very pleased of having today the speaker of this last colloquium of this year, that is Gigliola Staffilani from MIT in Boston. Let me just introduce her, just saying that she's the Abby Rockefeller Mount Professor in MIT. And well, she was graduated undergraduate degree in Bologna in 1991. Then she moved to University of Chicago, where she earned her master and PhD degree. And then she was first assistant professor in Stanford, and then she got the tenure position in Stanford and in Princeton, in Brown University. And then in MIT, in 2000, she moved to MIT in 2002. And she became, I guess, the second female to be hired as full professor at MIT in mathematics. She received really many several recognition awards. Let me just remind she was elected Fellows of the American Mathematical Society in 2012, Fellow of the prestigious American Academy of Arts and Sciences in 2014, and also Guggenheim Fellowship of the Simon Fellowship in Mathematics. And she's an expert of PDEs and harmonic analysis, and in particular with emphasis on nonlinear wave and dispersive phenomena, and she's a member of the famous so-called high team that is constituted by Colliander, Kiel, Tagoka, and Terence Tao. And she also an active member of the Association of Women Mathematics. We are really pleased and honored, happy to have with us Gigliola, please.
So first, thank you, Fabio, for the introduction. And I also have to warn you that I just flew from Boston, arrived around 1:30 today in Venice, and now I'm here. So hopefully I can stay awake. So in this talk, I would like to take you on a little bit of a tour of various results that have been proved in the last 15, 20 years. And that's why I titled it The Many Phases of Dispersive Equations, because I will show that how many different types of mathematics have been introduced to solve problems that at the beginning might look just they are purely from a physical point of view, considered from a physical point of view. So in fact, just to introduce a little bit the topics, I put together a bunch of pictures that, as for now, they might look kind of disconnected. So the first one is a little cartoon of a fiber optic. Then this one, if you are an harmonic analyst and you know about Perron tree, that's exactly an example of a Perron tree. Here we have laser lights. Then there is a rainbow. And down here again is something that looks not very connected to the phenomenon of waves, which seems to be a little bit of a theme here. In fact, what you see here is just an ellipse, and the dots that have been highlighted are points on the Z2, on the lattice of coordinates that are integers. And then there is a lake with a pebble been thrown in and various ripples that move on. And that's an example for me of what dispersion is in nature. And then waves, like this, the more typical ones are the water waves. And then the last picture is the picture of the Bose-Einstein condensation. So there are a bunch of pictures here, and throughout the talk I will highlight, and you will see the connection with some of them. Not all of them, but hopefully some of them. So as I mentioned, the kind of results that I will introduce today, and I apologize already because whatever I'm going to introduce is just the tip of the iceberg. There is a lot of work behind it, but I will only tell you some specific ideas on it. So clearly, harmonic and Fourier analysis are the tools that you use all the time if you want to study nonlinear PDEs, in particular PDEs that have waves as solutions, such as dispersive wave equation. A little bit unusual is the analytic number theory. And in fact, this connection between the two topics was made, as far as I know, by Bourgain, and I will explain to you where and how. Of course, the math physics, because we talk about physical phenomenon, dynamical system, probability, and the last one that I want to introduce, and I hope I have time. Fabio said I can talk for as long as I want, so I hope I will get there. So the probability and the symplectic geometry are the last two topics, and hopefully I can get to that point, at least to give you a little bit of a flavor where they come in. So in order to take you on this little tour, I wanted to consider a specific equation. But keep in mind that whatever I'm going to say is not necessarily only for these equations. It can be applied to other type of dispersive equations, also waves. But I wanted you to concentrate just on one so that you can keep thinking about that example. So what you see here is the NLS equation, nonlinear one. There is I, which is the complex, and then there is partial derivative with respect to t, and then the Laplacian, and then that's the linear part. And the right-hand side, I put the nonlinear part. So lambda is just, let's think of a constant plus or minus 1. And then the nonlinearity is cubic in this sense. So the function u is a function in time and space, x. And this is a Cauchy problem, or initial value problem, because I'm going to assign the value at time 0 of my wave. So you know the initial profile, and that's the function u0x. For the rest of the talk, the x is going to be in the torus of dimension d. And you might think that why do we care about studying the Schrodinger equation on a donut, but that's the reason is because really that's another way of saying that you take periodic data, which is actually very realistic. So x on the torus means that you're just taking periodic functions that are periodic, but the periods in different coordinates might not be the same. And this will introduce or will be relevant when I'm going to start talking about rational and irrational tori. And that will come later. So this equation comes from physics. In fact, in the next slides, I will give you an example of what is a physical phenomenon in which the Schrodinger equation comes in. But before we get to that, let me just remind you that this problem has two conservation laws, for sure. The mass, which is nothing else than the integral of the absolute value of u. By the way, the solution u for the Schrodinger equation is a function into the complex numbers. So we take the absolute value of u squared, that's the mass, and then the Hamiltonian, that's the energy, and it has a first piece, which is related to the linear part of the problem, which is the kinetic energy, and is the gradient of u squared. And then there is the potential energy, which in this case, because I'm considering the cubic NLS, is the power 4 of u. So this will be an L4 norm. And the lambda appears here again, was my plus or minus. And you can see that if lambda were negative, then there would be a competition between these two positive quantities. And in fact, in those cases, depending whether the kinetic energy, which is associated to the linear part, is more powerful than the potential energy, which is associated with the nonlinearity, or vice versa, the problem I have blow up. And I'm not going to actually go into those details in this talk, but that's important to know. But if lambda is plus 1, then clearly the conservation of the Hamiltonian gives you a bound uniform in time, both of the gradient square and of the L4 norm of the solution, which is actually very important, in particular when you want to go from a local in time existence, uniqueness, and stability to a global in time. So I promised that I will give you at least an example in which the Schrodinger equation comes in. And this example is related to the last picture that I presented at the beginning, which is the Bose-Einstein condensation. So let me describe a little bit what these pictures tells us. So the phenomenon is the following. You consider either a box or a certain potential that keeps together a certain gas. The gas is very diluted and is made of particles that are boson. Now, because the gas is diluted, the interaction between the particles is very small. And the phenomenon we wanted to study is what happens as you lower the temperature to the absolute zero. So a low temperature, instead of thinking of the gas being governed by sort of billiard balls interaction, we think of it as interpreting each particle of the gas as a little wave packet, and then study that. Now, if the temperature is low but not too low, the amplitude of the wave packet and the distance between the wave packets are not comparable. The amplitude is much smaller than the distance, and hence there is not much interaction again. But as we move the temperature down, we're going to reach a certain critical temperature in which the amplitude of the wave packet and the distance of the wave packets are proportional to each other, and hence there start being interaction. And what happens is that each of the wave packet, which was behaving sort of independently with its own dynamics, they lose this identity, and they all coalesce as t goes to the zero, absolute zero, into this giant wave matter. Now, the mathematical description of this phenomenon, I'm going to go next slide, actually it wasn't, in dimension 3 at least, was reached not too long ago, in fact around 2007, by a team of Erdős, Schlein, and Yao, H.T. Yao. And so basically what happens is that you have to take a limit. And as you know, the limit is always hard, especially in this kind of context, because you have to go from a certain phenomenon like particles to another phenomenon, which is the Bose-Einstein Condensation. And the tools you use to study these two things are different. I'm going to spare you how that goes, that limit. But what's important to recognize is that what you face is the following. There is first the description of the little wave packets interacting. That's given by the BB-GKY hierarchy. And I'm sorry, I don't remember the names of the BB-GKY. And then you take the limit as n goes to infinity. So instead of taking the temperature that goes to zero, we take the number of particles that go to infinity, but the two things are related. And we reach something called the Gross-Petaviesky hierarchy. Okay, so I have to say that in this problem, it's hard to take the limit, but even harder is to prove that the solution of the Gross-Petaviesky equation is unique. That's really hard. So I decided not to write down the hierarchy because it's just a bunch of symbols and it will be meaningless at this point. But I wanted to make the connection with the Schrodinger equation. So if you think about the following vector, so this xk is the vector x1 to xk, where each of the entries is itself a vector, is the position, if you like, of the particle, either in RD or on the TD, if you are in a periodic situation. And let's consider a very specific initial data for the Gross-Petaviesky, and in fact is a product of functions. And this is not the only type of initial data, okay? But in order to understand the connection with Schrodinger equation, that is what I'm assuming. So this is, don't worry exactly how it looks like, but it's a function. Think of it as a function. And it's written as a product of U0, indexed by the J1 to K. Now, we feed this initial data in the Gross-Petaviesky hierarchy, which is an infinite system. And what we discover is that the solution is going to be given by this gamma, k, which now depends on t. And it's again the product of now functions that depend on t. And the connection between the u0 and the u is that these u's are solution of the Schrodinger equation that I introduced at the very beginning. So that's the connection. And actually, it's not hard to see that this is the solution, the Gross-Petaviesky. Once you make this connection, it's pretty easy. You do the calculation, you check the solution of your Gross-Petaviesky. The point that I want to make here is, again, what I said before, that it's hard to say that this is the unique solution. And that actually has been proved. And I wanted to remind you of a few people that worked on this. The work of Erdős, Schlein, and Yau, and that comes, for example, from Spahn. Then I did some work with Kirkpatrick and Schlein in the periodic case. And then there is a team of Chen and Pavlovich at UT Austin, and another Chen and Holmer at Brown that have been looking at this more in recent time. But I'm going to stop here. This is a very active area of research. I want to say just one thing that I'm doing recently on that, and it's the following. If you consider the situation in which the space dimension is 1, in particular, let's take our favorite equation, that's the Schrodinger cubic plus or minus in 1 dimension, so either in R or in the circle. It is very well known and has been known for a while that this is an integrable system. And if I ask any of you what an integrable system means, you will give me a different answer, because there are many different ways of interpreting what integrability is. But one can think about lax pair, inverse scattering. There is a lot of geometry going on if you look at the work of the geometer, like Smell, for example. But one expression that I guess we all agree upon is that this problem admits an infinite number of conservation laws. We already saw 2 of them. It was the L2 norm, that's the mass, and then there was the energy that has the gradient in there, but you can generate an infinite number of conservation laws that have as a main term, or the higher order term, something that like a piece that looks like 1/2 gradient of order s squared dx, and then lower order terms. So with actually here is a bunch of women. So my former student, Dana Anderson, Andrea Namod, and Natasha Pavlovich, and myself, we were wondering, where does the integrability of this system come from when you take the limit? What's up above? So you have the system of particles, you have this intermediate system, which is BBGKY, which is a little wave packets. Then you have the GP, ARK after you take the limit, and you have the Schrodinger equation. So where does the integrability comes from in this limit process? And it was actually interesting for us to see that, in fact, the Gross-Petevetsky hierarchy has integrable, infinitely many conservation laws. That's all we could prove at that time, but now we went back and tried to see what we can say more in terms of inverse scattering, things like that, and we are working on that. But the paper that we have out is only about the conservation laws. Okay, now let's go back to our problem. Once you identify a certain PDE that, according to your understanding, should represent a certain phenomenon, first thing you try to do is whether it's well posed. And with that, I mean existence of solutions, uniqueness, stability, all that kind of stuff. So we want to do that today. And I'm going to start with my problem that I introduced at the beginning. And for now, it's not important whether x is in R or x is in a circle or a higher dimension donut. We're going to get to that. The 2 problems are very different, and we're going to get to that in a moment. But at this stage, what I want to do is change this initial value problem here with something which requires less regularity. Because if you want to interpret this equation as it's written, then you have to have 2 derivatives in x, which takes you outside of the conservation laws, which have just the L2 and the gradient. Okay, so you would like to stay within these conservation laws because that's more physical. So we change that into an integral equation, and this is via Duhamel. Of course, here I put double arrow, but it's not quite right, because of course here you need more derivative, and here you need less, but modulo that. So you can write your solution as the linear part, that's the Schrodinger group acting on U0, plus a nonlinear part here, which is written with the Schrodinger group acting on the nonlinearity. Now, of course, this doesn't tell you that you solved it, because it's you express U in terms of U. So, but the way it's written tells you that maybe what you can look at is the right-hand side and call that an operator applied on U, and then look for a fixed point. So then you can use a bunch of fixed point theorem that you can define in your favorite Banach space or even more general stuff. So basically what I want to say is the solution of the Cauchy problem I'm going to reduce to the fixed point of an integral equation. I mentioned that ST applied to U0 is the solution of the linear problem. In other words, it just solves this guy here, which is completely explicit. And I'm going to get to that. So now, you know that when you wanted to prove that there is a fixed point, let's say you want to prove that your operator is a contraction, then the first thing that you want to do is understand what is the space where the fixed point could happen. And going back one slide, and here you see that, there is the linear part, and then at least intuitively, if t is very small, then this piece could be interpreted as a small perturbation of the linear part. So in order to identify your space, what you do is you try to prove as many estimates as possible for the linear operator. And now where the two things diverge. So let me say that understanding, so by the way, the solution of the problem is completely explicit for the linear part, okay? I wrote here what happens when we are in the periodic case. I'm going to go back to it, but you can have similar thing expressed instead of a oscillatory sum, it's going to be an oscillatory integral in RD, and oscillatory sum in TD. Now, if you are in RD, it has been known for a very long time that the adjoint of the linear solution of the Schrodinger equation is actually the restriction of the Fourier transform on the paraboloid. If we are talking about Schrodinger on a cubic, we are talking about KdV and whatever other surfaces. And there are many theorems starting from very important people, Stein, and then of course Bourgain, Wolff, and so on, and Territau as well. Many theorems that tells you that you can actually restrict an L2 functions on a curved surface, if it's curved. If it's not curved, you cannot do that. And there are many estimates, and that's what you use to build up the space where you then look for the fixed point. Now, when you are in the torus, and by the way, all those theorems of restrictions have a very fundamental tool that you use, which is the estimate of oscillatory integrals via basically integration by parts. Now, when you have the situation of the torus, well, this is the expression of the solution of the linear. This is a sum, and it's an oscillatory sum, and you cannot integrate by parts. So until basically Bourgain 1990 or a little bit after that, right before he got the Fields medal, really people didn't know how to estimate this, because this is an element that is studied in analytic number theory. That's the connection with analytic number theory. So let me try to explain a little bit what we do or what has been done. So let's take a specific dimension, dimension 2. That's the first interesting dimension. If you are in dimension 1, there is only one period that's not interesting. So let's take dimension 2. And let's also, I'm telling you, in this estimate that you want to prove, this is called the Strichartz estimates, let's take Q equals 4, which is also an index that it's the Strichartz estimate in R2, which we already know. And what we want to prove is that the L4 norm, both in time and in space, but look, this is time on an interval, not on the line, which is what happens in Rn, because we have dispersion. So here you have to restrict on an interval time. So this L, in this case L4 I'm looking at dimension 2, is bounded by a constant times the initial data in some Sobolev space right here. So this is the estimate I want. The equivalent estimate in R2, where dispersion happens, and with dispersion I mean that the amplitude of the solution shrinks to 0 as t goes to infinity. In that case, when Q is 4, and we are in dimension 2, so here we put R2, here we can take the whole real line, because this decreasing to 0 allows you to integrate on the whole real line in time. And on the right-hand side here, instead of HS, you actually have the mass, L2. So that's what happens when you are in R2. But in the periodic case, we do not expect that to happen because there is an interaction with the boundary. And so the nonlinearity keeps, messing up your signal as you go forward. So what can we do in order to get something like that? We are willing to pay with some derivative if necessary. So this brings us to the distinction of two types of tori. The first type of torus that I wanted to talk about is the rational torus. What that means is the following. So when you take the Laplacian and you look at its symbol, that's going to show up here. It's going to be here. And the alpha 1 and alpha 2 are positive numbers which are connected with the periods. I think it's 1 inverse, then divided by 2 pi, whatever. Never mind that. But this alpha 1 and alpha 2 are positive numbers, both positive. Positive, but I'm going to describe this torus to be rational when the ratio between this alpha 1 and alpha 2 is a rational number. In other words, when the ratio between the two periods in two different directions is a rational number. And then the other case, of course, is when the ratio between the two is not a rational number. So let me explain a little bit why the two things are different. In the Bourgain's proof, which was done in 1990, he used actually the square torus. But you can repeat the argument if you are in the rational case, meaning that the ratio between the two indices is the two alpha 1 and alpha 2 is a rational number. So let's consider the situation in which we have the rational torus. And let's think of alpha 1. You can reduce the whole thing by assuming that alpha 1 and alpha 2 are two integers. They're supposed to be positive, so 1, 2, 3, whatever. And this is the expression of your linear solution. And now you notice immediately that if alpha 1 and alpha 2 are integers, then this expression is not just periodic in x, that you can see here, but it's also periodic in time, t. So when you go back to your estimate, you replace the interval 0, 1 with a circle again. It might be, okay, not of length 2 pi, but don't worry about that. So here you're going to put the circle because now you know that it's periodic also with respect to t. And here is your rational torus t2. And he proved that indeed there is an estimate for this L4 norm, but you have to, instead of putting here the L2 norm, so the mass, you had to pay with a little derivative, so epsilon. As long as you put epsilon strictly greater than 0, then you're okay. So let me, actually the proof is not hard. And the way, it's not hard after you understand, like everything that Bourgain does. It's not hard after you really know what to do. So what you do is you have an L4 norm. You write it as a product of two functions in L2. You use Plancherel. The product of function becomes convolution. You write it down, the whole thing. You use a Cauchy-Schwarz. And at the end of, while you do that Cauchy-Schwarz, what you have to count or measure, if you want, is this set. So you have to tell me how many n, this is a vector in Z2, so will be a point in the Z2 lattice. How many n are such that I can write alpha 1 n1 square plus alpha 2 n2 square equals some r square. So this is my set sigma. So how many n can be written like this for fixed r, and of course for fixed alpha 1 and alpha 2? Well, that corresponds in the counting how many lattice points sit on the ellipse. The ellipse has this, if alpha 1 and alpha 2 were 1, it would be a circle. But if not, it would be not a circle. And you can rephrase this by saying, in how many ways can I write a square into sum of squares where alpha 1 and alpha 2 are natural number? And that actually been estimated by Gauss. So this is a Gauss lemma in elementary analytic number theory. And the estimates in terms of R is that this measure, or this number of lattice points, is basically like exponential, some constant log r of log r. In any case, much smaller than r to the epsilon, where that's where the epsilon comes in. That's the h epsilon that I put in there. So this was the contribution of analytic number theories in forming harmonic analysis in this work of Bourgain. Now, what happens when you have, instead of a rational torus, you have a torus in which the, the periods are not the ratio of the periods is not a rational number, which obviously can happen. Well, there was nothing for about 24 years. And then 2014, Bourgain and Demeter settled the whole thing. And they proved similar estimates. And here now, because the time is no longer periodic, because if you imagine putting that expression instead of an integer or natural number, you put a square root of 2, you don't have periodicity in time anymore. So you have to cut with an interval 0, 1, say. And they proved exactly the same estimates. Surprisingly, analytic number theory had nothing to do with their proof. The proof is purely harmonic analysis, very hard harmonic analysis, and is based on the resolution of the L2 decoupling theorem. So this was a major conjecture in harmonic analysis, and it is connected with what I mentioned before, which was the restriction of Fourier transform on surfaces that have a curvature. Now, I did some work. The Strichartz estimate alone actually is not enough to prove well-posance. You have to do some refined bilinear Strichartz. I did some work with my student Fan and my another student, Wang, who is a student of Larry Guth, and my postdoc, Bobby Wilson. And then an interesting thing that happened is that actually Yu Deng and Pierre Germain and Larry Guth proved that it's true that you have the same estimates for irrational tori, but actually what you can prove is that the Strichartz estimate in irrational tori happens for a longer period of time, which is kind of intuitively true, because if you think about having a torus which is irrational and the wave incoming hitting the boundary, it's not going to hit back on itself after final many attempts, but it has a little bit more room to spread. So it's like to say that there is some kind of little dispersion happening that allows the estimates to hold for a longer period of time. And that was quantified very well from their work. But what's even more interesting, I found, is that some sharp decoupling on curves allowed actually Larry Guth, Bourgain, Demeter, and Larry Guth to prove a very important, or to prove a conjecture that was very important in analytic number theory, which is the Vinogradov mean value theorem. And so as we are now, harmonic analysis is informing analytic number theory, so it's going in the opposite direction. It's actually a very beautiful topic, but I don't have time to go through it, but that's where we are now. Okay, now let me go back to the original Cauchy problem that we had. I give you an idea how you build up the space where you can conduct your, for example, contraction mapping theorem. You can use that. And then you can prove that this problem has local in time for any lambda, either plus or minus. You can prove that there is a solution unique, and there is stability and everything, as long as you take initial data that are in HS for S strictly greater than 0. Remember this for the end of the probabilistic part that I'm going to talk about. This fact, the S strictly greater than 0, depends on the epsilon, or the estimates R to the epsilon that I mentioned before. The fact that you have to use a little bit of derivative to have your L4 estimates. But of course, if lambda is 1, then we have the nice bound of the Hamiltonian that has a plus sign between the gradient and the L4 norm. And you can use an iteration argument, and you can certainly prove that you have, for lambda equals 1, that's the defocusing case, global solution. So you have a solution that exists for all times. And you are assuming that S is greater or equal than 1 because you want to start from the Hamiltonian, where the H1 norm is part of it. There are a little bit stronger results, a little bit below 1 with the I method, but I'm not going to go on that, because what I really want to think about is the following now. Now I know, at least if I have a smooth enough initial data, I have a global solution. And if you are in Rn, then the dispersion actually tells you not just that you have a global solution, you can say that as t goes to infinity, this global solution becomes linear. So there is a so-called scattering. So your nonlinear solution as t goes to infinity behaves like a linear one. But in the periodic case, this is not the case. This is not true. You don't get scattering in the periodic case. So the question is, what's going to happen as t goes to infinity? What happened to the solution? Can we measure something or some kind of dynamics that happens? One of the questions that people are interested in is studying the transfer of energy, which is a concept which is related to also weak turbulence, which is not just for Schrodinger, it's also for fluids and all of that. So let me give you my version of very, very weak turbulence in this context. So what I want to study is the following. At time 0, let's assume I'm giving you an initial data, and what I'm representing here is basically the initial data but in the frequency space, not in the physical space. So I'm representing it like a little bump near frequency 0. So what you see here, the green graph, if you like, that's the absolute value of the Fourier coefficient of your initial data squared. If you think about it, when you integrate this, you get the mass. So as t changes, the area of the subgraph stays constant. Okay, that's a fact. But still, we would like to know whether this signal, which at time 0 was concentrated frequency-wise near 0, as t goes to infinity, moves to very large frequencies. So this is the transfer of energy from low frequency to high frequencies. One thing that I just told you is that this might happen, but there is a very rigid structure. It cannot happen like in any wild way because the graph of the area of the subgraph has to be constant at each time. Then I didn't put in the picture the fact that also the energy has to be constant. That puts even more constraints. So it's very hard to understand if there is this movement from low frequency to high frequencies. And how do we measure that? Another thing that it's even harder is if there is such a transfer from low to high frequency, is it going to happen in a kind of disordered way, like in this picture, like you jump too high and then maybe you jump a little bit back and then you go forward, blah, blah, blah. Or it happens in this very nice decreasing way. That's even harder, and we have no idea at all what happens here. So what I wanted to address in the next few slides is just the first question. Can we measure whether there is a transfer from low frequency to high frequencies? One way of investigating that, and certainly this is not the only way, is if I'm trying to understand whether this piece grows as t goes to infinity, meaning it goes towards c large, then what I do is I hit this object with a weight that is going to emphasize this movement to high frequency, right? And then I'm integrating it. And why am I doing this? Because really at the end of the day, this is nothing else than the Sobolev norm, HS. So you might have heard about understanding the growth of Sobolev norms at t goes to infinity. This is because if there is such a growth, then we know that the function as t, the Fourier coefficient, if you like, move from low to high frequency. So we are interested, after I made this connection, understanding the limit as t goes to infinity of the Sobolev norms. And here we are looking at a smooth situation, so S is large, okay? S is not small. A trivial bound in time is given to us by the local well-posedness going to global, so the iteration. So first we know what happened in interval 0 to 1, and we have a bound in the sense that the solution at time 1, it's, let's say, twice as big at time 0. And then you move again of time 1, then becomes twice as big as the one before. So this gives you a very trivial exponential bound. Can we do better than this exponential bound? Well, there are a few things that we wanted to say that, that we know where there is absolutely no growth whatsoever. The first fact, or the first case, is when, remember I mentioned the 1D cubic NLS, also the KdV. They are integrable system, and I gave you an idea how this integrable quantity look like. They always have the gradient to a certain order square plus lower order terms. And if you combine them in the right way, then you do have that any HS norm is uniformly bounded. Of course, depend on the HS norm of the initial data, but it's uniformly bounded. So integrability prevents this growth. Hence, there is no movement from low to high frequency. Another fact that prevents growth is what I mentioned before, scattering. Well, this is what happens in, like I mentioned before, when we are on the plane instead of on the torus. Because we know, and by the way, this is a very recent result. It's kind of easy to state, but it was not easy to prove. This is from Dodson in 2016. So if you have, if you look at the R2, and again, same problem, cubic NLS, then we know that there exists a U plus. I'm talking about t goes to infinity. There will be a U minus if you go to minus infinity. So there is a U plus in HS such that the solution of the nonlinear problem U minus the linear evolution of this U plus as t goes to infinity goes to 0. This is scattering. And of course, this fact prevents growth. Why? Because if I'm looking at the HS norm of U, I sum and subtract this linear evolution. Now, this guy is small. If t goes to infinity, that's scattering. And this guy is actually the same normal U plus because the Schrodinger group is unitary. So you have a uniform bound. So on the plane, dispersion prevents this movement from low frequency to high frequency. So we go back to the torus. And I'm going to give you a bunch of facts. So the fact one is that, and this was proved by Bourgain, and also a student of mine, Fourier, gave a different proof. If you are in T2, you can prove this for other dimensions, but let me just say what happens for the problem that we have been looking at, the cubic in T2. Then you have a better improvement, the better estimate than the exponential. And so in HS, it goes like a polynomial, and this is the degree of the polynomial. Now, very recently, this is a result by Deng and Germain, which is a companion of the fact that the Strichartz estimate live for a longer time if you are in the rational torus. And what they proved, so they are in a different dimension, T3, a generic tori. Generic here means that if you have periods in the three different directions of the torus that have a certain Diophantine condition, then you can prove better polynomial bounds. In fact, they are looking only at the H2 norm. You can do for HS, but that's not important. And this theta p here, it's what you have extra if your torus is irrational of a certain type. So this it's connected with what I talked about before of the longer Strichartz estimate. Okay, so and now the two results I just presented, it tells you at most how much it can grow. But then a very, very relevant question is, does it grow at all? We know that there are constraints, the mass, the energy, and so on. So can we exhibit at least a solution that grows? So there are two theorems in this context that I want to mention. The first one is an older theorem with the I team, Fabio talked about before. It says the following. It doesn't prove that it grows, but it says if you give me a sigma, which is measured as small initial data, you give me a k, which is very, very large, then there is a time, which is also itself very large. There is an initial data which is smaller than that delta, not sigma, so I wrote the delta here. There is an initial data which is smaller than that delta, and if you wait long enough, the HS norm, this is the HS norm, I forgot to put the sign here anyway, so the HS norm is larger than k. So this tells you that you can construct a solution which is a small norm at time 0, but if you're willing to wait long enough, it gets big. What we don't know is what happened after time capital T. It might go back. We don't know that. We cannot prevent that from happening. I mean, at least we don't know how to do it. And one thing that I want to remark is that this theorem is for rational torus, okay, rational. There is another theorem by Carl and Fau, which is a little bit more numerics, and they actually construct a solution that at time 0 lives just in these 4 frequencies here. But if you wait long enough, you can find something as far as you want from the origin. Something small, but it excites frequencies which are far from the origin. Both of these cases are for rational tori. Also, this result of Carl and Fau is rational. So let me give you a little bit of a flavor of the first result that I mentioned, the one I proved with the I-team. Remember that you want to construct a solution. We are not proving this for every solution. So I have a little bit of a freedom of how I want the solution to look like. And the way I'm going to describe it is in this way. We are in the periodic case. We are in the rational case. Think of, for example, just the square torus to make things easy. So the way I wanted to describe my solution is a sum of A and T, and then this will be the part that will appear if you have a linear solution, and here you have just independent of T, and then this will be just linear solution. So all the fact that I'm thinking about nonlinear problem comes from the fact that this coefficient depends on time. Then you plug into the equation, and you get a relationship among the coefficients, which is this. This is derivative of I, derivative of T of AN. Actually, this could be like a really dot, because only depends on T anyway. This comes from the nonlinearity, and here is the interaction. And this gamma is made of the following. Are all the n, n1, n2, n3, such that n1 minus n2 plus n3 is equal n. And this omega here is n1 square minus n2 square plus n3 square minus n4 square. And if omega were 0, that means that I have a 4-wave interaction and in resonance. Okay, so that's omega 4 equals 0 means that I have 4 waves in resonance. This system is way too huge to study in a dynamical using dynamical system arguments, so you wanted to reduce it. So you want to make a bunch of restrictions, which I'm not going to write here. And the restriction is, well, you think that the growth might come from resonance, so you will pick omega 4 equals 0 all the time. That's still an infinite system. You want to restrict further, and what you do is you construct a very specific type of set of frequencies that have nice behavior. And once you do that, and I'm skipping a lot here, you come up with this toy model. Now, the danger is that if you make too many constraints, you might not be connected at all with the original problem you were trying to study, okay? So you have to balance the two facts, and in fact, we prove that the solutions of this toy model is actually representing the solution of the, it's not the same as the solution of the original NLS problem, but it's very close to it. And all the growth that happens will come from here, because the difference between this and the one I want to look at, really, it's very small. Okay, so now this is a lot more manageable, and especially because in the nonlinearity, you have a nearest neighborhood interaction, while before you had interactions everywhere. So let me show with a picture what the dynamic is. Because of the conservation law, the L2 conservation law, the whole dynamics work behaves or happens in this big sphere. These x's are vectors in Cn, so they are complex vectors. And the whole dynamic is here because if you really write this down, this is like to say that you fix the mass to be 1. So everything happens in there. But there are these large circles, tau 1, tau 2, and tau 3, which corresponds to the vectors in Cn where you fixed one of the coordinates to be of size 1 and everything of size 0. This large circle that basically looks like in this picture are actually invariant with respect to the dynamics of the problem. And what you would like to do to say that something grows, and you can see that specifically, is that you start at T1, this corresponds to low frequency, and you want to move to tau n, that corresponds to high frequencies. And because these circles are invariant, you have to be very careful, because certainly you cannot start on top of the circle because you keep rotating there. You're not going at all here. So what you want to do is you want to start close to this circle and manage to go and avoid all these other obstacles so that you get to the end right here. Okay, so I have a picture, fortunately. And in fact, that's the theorem. We can say that we can start close to this invariant circle here and move and avoid everything and go to the end. And that's really is going from low to high. there has been a much better, so when we wrote this paper, we did it by hand, and then the dynamical system people, like Guardia Kalosh and House Purchase and other people, they actually did a lot better than us, and there is more. So some remarks is that you don't see here where the assumption of being a rational torus comes in, but if you zoom in, you see that. And then our question that I asked with my postdoc, Bobby Wilson, was what happens if the torus is irrational? Does the same kind of dynamics work? And the answer is that no, you cannot do that. In fact, the construction of that set that was growing in a certain sense, that solution that was growing in a certain sense, will not happen if you have the irrational torus. This does not mean that there is no transfer of energy in the irrational torus. It just means that it's harder to prove, in my view. This is a slide in which I want to say that there are a bunch of results on this topic, and there is a lot of work going on, and more papers are happening. Well, you can read them. So there is, like I mentioned already, people above, then Gérard Grelier, they don't look at the Schrodinger, they look at the qubit Szego, and they do a beautiful analysis. Then there is a very nice paper, Hani, Posador, Tsetko, Vishilia, in which they actually prove the growth, but the manifold or the domain of your problem is R cross T2, so having an R helps. And then there is Faour, Germain, and Hani. This is the large box limit. It's really interesting, and it's much more related to wave turbulence than what I said, and so on. And there is more, but okay. Now, I wanted to present a couple of more facts that are connected to different kind of mathematics. So one is the probability aspect of it, and the other one is something related to symplectic geometry. So let me first analyze a little bit how we go from the equation that we have to a system which is actually an infinite dimension Hamiltonian system. And once we have an infinite dimension Hamiltonian system, then it comes natural to ask if those kind of deep theorem that happens in finite dimension Hamiltonian system can be transported in the infinite dimension. And there are a lot of issues, of course, on that. So let me first start with the equivalence of this initial value problem with this infinite dimension Hamiltonian system. The equivalence is trivial, so you pass from here to here just by going from the physical space to the frequency space. So you take the Fourier coefficient of u, and you write it into the real and imaginary part. That's the real part I'm going to call it an, the imaginary part I'm going to call it bn. And if you just work it through, you see that the infinite vector an bn satisfy an infinite dimension Hamiltonian, where h is exactly the Hamiltonian I mentioned before at the beginning, the kinetic plus the potential part. So our theorems that are true for the finite dimension are also true for the infinite dimension. And of course, it depends on the theorem. So let me give you a couple of theorems. So the first one has to do with non-squeezing. So this, I recall here, the famous theorem of Gromov is the finite dimension one. So assume that phi of t is a Hamiltonian flow in R2D. 2 because, okay, the vector is usually like p and q, so that's why I put the 2 right there, which is also a symplectomorphism. Okay, there is a symplectic form in there that you can define. I'm not going to go into details, but for those people who know, good. If not, don't worry about it. Now, let BR be a ball of radius r, little r, in your finite dimension space R2D. And let's call C capital R the cylinder in the same space. Now, if the flow of BR gets into the cylinder, has to be that the radius of the cylinder is bigger than the radius of the ball. That's what the theorem says. Now, we know, going backwards, that I can describe, for example, my NLS as an infinite dimension Hamiltonian system. And for that, you can define the ball, you can define the cylinder, it's just an infinite dimension thing. So can you say the same? Can you prove the same non-squeezing theorem. So let me tell you a little bit of what we know. So the first, I mean, a lot of work on this has been done by Cookson. He really formalized this nicely. And he proves that if this, the dynamics of the flow is a compact perturbation of the linear, so for example, if you take a compact perturbation of the linear Schrodinger flow, then this is true. The point is that the nonlinear Schrodinger is not a compact perturbation. So all of the regular Schrodinger equations that we look at do not fall into this category. But it is true for the cubic defocus NLS in T, just one dimension, where the symplectic space is L2. Bourgain proved that. And then we were working with KdV, and the H minus a half is a symplectic space for the KdV. And we thought that just by using the same argument that Bourgain had, we could just claim the same for the KdV. And actually, it's not true. The fact that the KdV has a quadratic nonlinearity and the NLS that Bourgain uses a cubic nonlinearity really is a big difference for the argument. We still proved it, but never mind. It's not a direct proof. I still don't like it, but anyway, it's true. There's a partial result about the Klein-Gordon equation, but the flow itself in the Klein-Gordon equation that lives in the symplectic space, it's an almost sure flow. There's some probability in there. So it's a flow that exists for initial data of a set of measure 1, whatever that measure is. And then my student, Denham Anderson, has some partial result of that. And then true for the cubic defocus NLS in L2, but R2. It's not periodic, so it's not quite an infinite dimensional Hamiltonian system the way I said before, but this is a result of Kilip, Visan, and Zhang. And the reason why we don't know what happens in L2 if you put here the torus of dimension 2 is because you remember, in order to have the flow, you have to have HS, S greater than 0, so you just skip L2. But that's more or less what we know, and would be good to have more. I have now the probabilistic part, but I can stop if we want to stop. So, you want to see that? Sorry, it's his fault. Okay, no mind. Okay, so the last part is about the probabilistic approach. I already mentioned the almost sure flow, so it's something related to that. And I'm going to look a little bit about the Gibbs measures, and I will do very quickly. The finite dimension part of the Gibbs measure is trivial, because in the finite dimension, if you look at this Hamiltonian flow here, we are in finite dimension. We know that it preserves volumes because the Liouville theorem. So if you take the flow here and you take a set A, then the volume of A is the same as the volume of the evolution of A for any t. Now, the volume is a certain measure. I want to define another measure, which I'm going to call Gibbs measure, which is made by the volume here, but also e to the minus the Hamiltonian. 1 over z is just a normalization because you want to make a probability measure. Anyway, not important. This is also invariant because the volume is invariant from Liouville's theorem, and this is invariant because the Hamiltonian is invariant. So the Gibbs measure being invariant in finite dimension is trivial. But now let's see what happens in infinite dimension. Again, I'm going to take the same problem that I had before, and you know how to transform it into the infinite dimensional Hamiltonian system. I can tell you right away that just taking the nonlinearity cubic here is not going to work. You have to do a process which is called weak ordering. So you have to weak order the Hamiltonian. I'm not going to go into the details, but I'll show you in a moment what that really means practically. But replace the cubic with a nonlinearity, which is also cubic, but certain frequencies have been removed. Really, that's what's happening. Now, can we define here the Gibbs measure? Well, I put here in quotation mark because this means nothing, really. Because if you look at the volume, that's an infinite volume. It's not going to work in any ways. But nevertheless, you can, and I explain you briefly in the next slides how you do that. So the existence of the Gibbs measure, it goes back to Leibowitz, Rose, and Spear in 1D, and Klim and Jaffe in 2D and 3D. But what's interesting is, so there is a Gibbs measure, but can you prove that the flow keeps this measure invariant? That's the main question. And that was done by Bourgain. So I'm going to shrink in one slide a lot of work here. But basically, the theorem Bourgain says the following. Let's consider this NLS. We replace nonlinearity with a weak order nonlinearity, whatever that means, I'll show you in a moment. And let's take the torus, and also it takes the rational torus, actually the square torus. Then there exists a set, sigma, which lives in the support of this Gibbs measure, which you can, if you go through the argument, you notice that is of regularity no more than h minus epsilon, where epsilon is strictly greater than 0. So there is a set which is here, the measure 1, Gibbs measure 1, and for any u0 in this set, there exists a global solution, so for all times. Moreover, mu is invariant. Now, this is a hard theorem for many, many reasons, but for one reason is that this set here is in h minus epsilon, while we know the well-Poisson is in h plus epsilon. So we don't even know that there is a flow. That was the work of Bourgain, in fact. And I'm going to give you an idea why he could do it. So the initial data, that is the typical element that lives in the support of this Gibbs measure, this was known from before, from the people who constructed, looks like this. So this is the initial data. So it's basically like 1 over n, but there is a random variable, gn omega, think of a plus or minus 1 taken randomly, and then of course e to the I n x to reconstruct. And if you do the calculation, you see that this is in h minus epsilon. And by the way, randomizing here does not make it in a better space, not in a better subway space. So it's very rough. And g and omega are independent integer distributed complex random Gaussian variables. So there is an underlying probability space here. So why, of course, if you try to say that using Strichartz estimate that this evolves, you can't because you are too rough. But on the other hand, you have the randomization. So let's see how we can use that. And here now I'm shrinking Bourgain's argument in one page, but if you look at the paper, it's quite a lot of pages. So one of the things that he has to do, he has to estimate this expression here in little L2 norm in n and little L2 norm in m. The n is the Fourier transform of space, m is the Fourier transform of time. Remember that if you take a rational torus, the time is also periodic. So you will end up looking at the little L2 in m, that's the time variable Fourier transform. And the expression looks like this because really what I'm writing here is the convolution, is the product of 3 linear solutions in the Fourier space. Hence, I have to do the convolution of each one of them. And then this is the fact, so I'm summing in this space, which means I'm taking n1 minus n2 plus n3 equals n. That's the convolution. I'm looking at the linear Schrodinger, so there is this constraint, m is equal to n1 square minus n square plus n3 square. Okay, this comes from the fact I'm looking at Schrodinger. The weak ordering just tells me that n1 and 3 is never equal to n2, which is going to be important in the next slides. Okay, so I have to do this expression, I have to take an L2 norm. How do I do that? Well, trivially, I write it down. So I'm taking the L2 norm square, so I'm summing n and m of this long expression square. If you are naive and you do the same argument that Bourgain does in the Strichartz estimate, you will do a Cauchy-Schwarz here, and you will lose the measure of this set, the set Sm. So this purple here is a loss of derivative, some order. But we completely forgot about the fact that we have these random variables. So let's try to make use of them. So I'm going back to here. So I'll write again the sum n and m and then f3 omega square. And now, in the next step, I'm going to use a large deviation statement or estimate that tells me that the L infinity norm of this guy is bounded by the L2 norm. Of course, not on the whole set omega, but in a smaller set. And basically, the complement of that set is very small. Here it is. Okay, if we do that, now we write the L2 norm, and I wrote it down here. And of course, everything goes out except the integral in omega of that. And now the fact that this n's, we can reorder them, so n1 and 3 is no equal to 2, can be used in order to, for the independence. And so at the end of the day, you end up with this. And the difference between this expression and this expression is this set here. And here you will lose derivative, while here you will not. Of course, there is this delta, but that's okay. It's not losing a derivative. So basically, this is the point in Bourgain's argument and many other things. But just wanted to give you a little bit of a flavor why he could do it, why he could say that there is at least a flow in that very rough space. And then the fact that he can go from a local in time flow to a global in time is because he keeps using the invariance of the set. So it can, it's a beautiful piece of work. So I'm done with that. I have some open questions that maybe some of the young people, or not so young, can try to look at. So one question that I'm really interested in is understanding the Strichartz estimates in a more direct manner, not as a corollary of the L2 decoupling. I know some young people are working on this, and this is really good because you need for later on for application. Improve polynomial bounds for the Sobolev norms. I gave you some examples, but we are very far. We expect something like maybe t to the epsilon, and we are instead t to the s, whatever. Understand embedding the dynamics in the rational and irrational situations. Seems that there are some differences, but that's not totally clear. Exploit harmonic analysis in analytic number theory. So if people are interested in number theory, you better learn some harmonic analysis now, because that seems to be giving you a really nice tool. I also have a more general proof of the no-squeezing. So all those theorems that I presented, they're all proved in a different way, in a sense. But the common theme is that first you truncate the frequency, you make a finite dimension, you apply the no-squeezing, and then you have to take the limit. And taking that limit has been an ad hoc argument for different problems. Would be good to have a larger one. And of course, also the I didn't add here, but there are a lot of questions, the probabilistic type of argument that I give at the end. So, thank you.
Thank you, Gigliola. It was really fascinating, this voyage between so different approach from harmonic analysis, number theory, analytic number theory, dynamical system. And so there are questions.
Anyway, you remember you mentioned at the very beginning of your talk that existence theorem for U not in HS. So my question is, does it hold for small norms of U naught or for large norms of U naught too? So for large initial data or only for small initial data? Yeah,
very good question. So these equations that we are looking at, they have some kind of scaling. So depending which regime you are, you can use scaling to make the initial data small. And that will be the case in which you are in the subcritical case. But when you are at the critical, supercritical case, that kind of argument doesn't work anymore. So the more recent theorems have been proved for the cases in which scaling doesn't help. So you really do have a large data, and you have to deal with that. So the first step usually is, let's make the initial data small or the time small. So then we can do the contraction. For contraction, you need to have something that's less than 1. So you do that. But then the question of long time dynamics, like for example the scattering, I mentioned that theorem of Dodson, that was in 2016 because it's a hard thing to prove. It's a long time dynamics that you have to do. So yes, now we understand that. And I presented mostly defocusing case in which you use the Hamiltonian or the mass in order to control long time dynamics things. But if you are in the focusing case, then there is another fascinating results about blow-up that happens, and the relationship of how large the mass is with respect to Q, which is the solution of a certain elliptic equation and all that stuff. That's a beautiful part of an argument as well. Yeah.
Further questions?
They're all tired.
If not, let's thank you again, Gigliola.
Thank you.
So, you are all invited to the refreshment on 7th floor.